Assalamualaikum. My name is Muhammad Ahmad Ashraf bin Muhammad Rozi. My metric number is AN220222. So I'm going to introduce the company profile. For our case study on process control optimization, we have chosen premium vegetable oil sodium bihide or PVOSB. PVOSB is a pioneer in the specialty oils and fat industry, established in May 1978. It operates as a subsidiary of Good Hope Asia Holding Limited. They are fully integrated, managing everything from crushing to manufacturing of bespoke oil and fats that meet strict customer specification. It is also important to note their strategic partnership with J Oil Mills from Japan, established in 2019. This collaboration allows them to offer premium fat product aimed at enhancing diet globally, while they have plantations outside of Malaysia. Their facility here focus heavily on palm oil processing and refining. So to understand where our project fits in, we first look at their general refining process, which is consists of 4 critical steps: degumming and earth bleaching. These initial steps are crucial for removing impurities like gums, metals, and color that compromise oil quality. Deodorization. This uses steam to strip away unpleasant odor and the volatile compound. Next is fractionation. Finally, the oil is separated to isolate specific fat component. Following this oil may undergo hydrogenation and chemical interesterification to modify its melting profile and stability before texturized and packaged for the consumer. However, the specific focus of our project is optimizing the bleaching and the deodorizing phases. If you look at the figure 1.4.2, which represents the P&ID for the bleach oil tank 101 system, you can see the current layout of the machinery. My group analyzed the critical components shown here, including the pump, heat exchanger, and especially the flow control valve. Currently, this system utilizes a standard configuration. Our objective was to identify areas within this P&ID where we could improve safety, efficiency, and cost effectiveness by applying sophisticated process control strategies, specifically moving the current manual of fixed control to automated PID driving system.
Hello doctor and good day everyone. My name is Durgeswari Muniyandi and my matrix number is CN240366 and I'm from group 5.
Good day doctor. My name is Jianjali Manimaran and my matrix number is CN240340 and I am from group 5.
Safety is very important in vegetable oil processing. The interlock and alarm system acts as an early warning system to protect the workers and equipment. Alarms alert operators when the condition like level, temperature and pressure exceed the safe limits. For example, a high level alarm prevents the tank from the overflow, while the low level alarm protects the pump from running dry. Modern refinery use advanced sensors such as ultrasonic, radar and pressure transmitters, which are more accurate and reliable than traditional float alarms. To prevent alarm flooding, standards like ISA 18.2 are followed, so only critical alarms are displayed. Smart alarm system can also trigger automatic shutdowns, improving plant safety and efficiency. Feed pumps are essential for moving oil and chemicals throughout the refinery. They ensure smooth flow and proper mixing and stable pressure. Different pumps are used for different needs. Centrifugal pumps for large flow rates and low viscosity oils. Positive displacement valve for thick oils and precise flow control. Metering pumps for accurate chemical dosing. Modern pumps used for variable speed drives which save energy and reduce operating costs. They are made from food grade, corrosion resistant materials to ensure safety and long service life. This is the example alarm system in the company. If anything goes wrong, this alarm will be triggered and will make sound. This is the temperature control system of the premium oil company. The heat exchanger E521 works in the bleaching section. It uses a network of pipes to control steam flow, oil flow and contents removal, which are important for the proper heating. The red pipes carry the steam from the high pressure steam boiler H5 HB521 to the heat exchanger. These lines uses the manual valve, so the operators must control the steam flow by their hand. The yellow pipes represent the process oil. The oil enters the heat exchanger, absorbs the heat from the steam and then flow to the next bleaching stage. After releasing heat, the steam state turns into the condensate. The condensate is removed by the green pipes, which are fitted to the steam traps. Steam traps allow the water to lift to the system while keeping the steam inside to maintain their efficiency. Before entering to the heat exchanger, steam passes to the flash vessel, which removes the moisture so that the dry steam can be used. Fuel oil is supplied to the boiler through the brown pipes to ensure the continuous steam production. In conclusion, the heat exchanger is very important for the heating in the oil. However, the system operates manually with no automatic temperature or flow control. This causes slow response, uneven heating, and operator error, making the process highly dependent on the human supervision. This is the example flow of heat exchanger E521's flow.
This diagram shows the flow of crude vegetable oil during the early processing stages. The process starts when oil is pumped from the storage tank into the system using a feed pump. The feed pump plays a very important role. It maintains constant pressure and steady flow in the pipeline. If the pressure is too low, the oil flow will slow down or stop. If the pressure is too high, it can damage the pipes and create safety risk. By providing the correct pressure, the feed pump ensures a smooth and continuous oil supply, especially when the oil needs to move to higher processing units. This prevents bottlenecks and keeps the process running efficiently. Once the pressure is stable, the oil flows through the oil heater, then the economizer, and finally enters the deodorization unit. Each of these stages is essential to produce a high quality and pure vegetable oil.
This is how they monitor the whole process and the pressure.
And now let's move on to content 2.3, which covers the overall process. In this section, we will look at how premium vegetable oil is processed, starting from the raw material stage all the way through to the bleaching process. Let's start with the raw material inlet and preheating stage. Feed pumps here control both the flow and pressure of the oil, ensuring a consistent supply throughout the process. The heat exchanger reduces the oil's viscosity, which improves mixing and makes refining more efficient. Temperature gauges are also installed to ensure the oil is heated safely without risk of overheating. Secondly, the bleaching process. In this stage, bleaching earth and activated clay are used to remove impurities such as color, pigments, trace metals, soaps, and oxidation products. It's crucial to maintain the correct temperature during bleaching, as this ensures maximum removal efficiency of these impurities. Besides, feed pumps play a key role in maintaining flow and pressure throughout the piping system. This prevents bottlenecks and ensures the oil reaches higher level units consistently. The flow rate must be carefully controlled, where too fast can reduce the efficiency while too slow can cause overheating. Operators monitor and adjust the flow as needed. Last but not least, temperature control is managed using the heat exchanger labeled E521 in our system. Steam is supplied through manual valves and any condensate is removed via steam traps. This ensures the heat exchanger operates efficiently and the temperature remains in the optimal range for all stages of processing. After bleaching, the oil passes through the filtration unit where bleaching clay is removed. The system is equipped with alarms that alert the operator if the filter becomes blocked, ensuring continuous and safe operation. Secondly, safety interlocks continuously monitor tank levels, pressure, and temperature. If any unsafe condition is detected, the system can automatically shut down the pumps to prevent accidents and equipment damage. Finally, the bleach oil is then transferred either to storage tanks or to the next refining stage, which is deodorization. Throughout this stage, the product is monitored for color, stability, and purity to ensure safe storage and to prevent product loss. This is the overview of the whole process.
For this part, which is content 3, Ahmad and I will explain it together. We have three types of alternative, which is interlock system, bypass in heat exchanger, and flow control system strategy in heat exchanger. I will be cover the first two alternative, and Ahmad will be continue for the last part. So the first alternative is interlock system. Right now, vessel V541 use two level switches, a high level switch and the low level switch. These switches only give on or off signals. They cannot show the actual level inside the vessel. Because of this, the system reacts slowly when the level changes. This can cause overfilling or low level problems, leading to the product loss, equipment damage, and safety issues. To improve this, a PLC-based control system is proposed. The PLC collects all level signals and control the system automatically. If an unsafe level is detected, the PLC immediately stop the operation and alert the operator. This makes the process safer and more reliable. From this slide, when we compare both systems, the current switch-based system is limited and depends a lot on manual action. So the PLC system is better because it responds faster, gives more accurate control, and reduces human error. It also allows easier adjustment of control system. Therefore, the PLC is the best option for this process. For the operating scenario, the focus is on the low level protection. If the liquid level becomes too low, it can damage the equipment. To prevent this, a level transmitter sends real-time data to the PLC. When the level drops below the safe limit, the PLC automatically closes a shutdown valve. For high level conditions, the PLC first gives an alarm to warn the operator. If the level keeps rising, the PLC automatically stops the filling process. This prevents overflow and ensures safe operation. Operators mainly monitor the system and only step in when it's needed. So, in conclusion, the PLC-based system provides better safety, faster response, and higher reliability compared to the existing system. Therefore, PLC is the best choice for improving vessel V541. Next, I will continue explain for the second alternative, which is the bypass in heat exchanger. This part focus on replacing the original manual bypass with an automatic bypass control system to improve temperature control of the bleach oil. From this slide, the original PNID shows the heat exchanger system used a static or manual bypass. This means operators had to manually adjust the system to control temperature fluctuation. This method is slow and depends heavily to the operator intervention. It can cause unstable temperature control and increase the risk of overheating or overcooling the oil. To improve this, an automated bypass system is proposed. This system uses a three-way bypass control valve or a controlled bypass line. Part of the cold process fluid bypass, the pass heat exchanger, and mix with the heated fluid at the outlet. By adjusting this bypass flow automatically, the system can achieve the target outlet temperature more accurately and quickly. This approach is faster than adjusting alternative state control like steam flow and help maintain better thermal stability. The bypass system improves flexibility by allowing the fluid to either pass through or bypass the heat exchanger. By controlling how much fluid flows through each path, the system can respond quickly to the temperature changes. One important design factor is the bypass flow rate. A properly selected bypass flow rate improves system responsiveness and keeps temperature control stable. It also increases system rangeability, meaning the heat exchanger can operate effectively under different flow rates and thermal loads. As a result, the system becomes more flexible and reboots during process fluctuation. For operating scenario, originally there is no temperature stabilizer after the oil exited the heat exchanger. If overheating occurs, it could damage the pipelines and downstream equipment. With the bypass system, a portion of fluid bypass the heat exchanger and mix with the heated fluid. This mixing helps control the outlet temperature and prevent overheating. Temperature sensor and controllers are installed to automatically adjust the bypass valve. When the outlet temperature is too high, the bypass opens to allow more cold fluid to mix in. When the temperature is too low, the bypass closes to increase the heat transfer. This automatic control provides faster response, stable temperature, and safer operation. In conclusion, replacing the manual bypass with automatic bypass control system improves the temperature control, energy efficiency, and operational flexibility. Therefore, the bypass system is a suitable improvement for heat exchanger E521 in the bleached oil process.
So I'll be presenting the proposed alternative for the control system improvement within the premium vegetable oil industry, specifically for the bleach oil PNID. If you look at the simulation diagram on the screen, our primary goal is to move away from the inconsistency of manual valve. To achieve this, we introduce automatic control valve at a key flow point, specifically at point P-3 and P-6. We utilize the automatic butterfly valve, as mentioned in our report. Butterfly valves are ideal here because they handle large flow effectively. This will be driven by pneumatic actuators, chosen for their speed and reliability, allowing us to modulate flow instantly rather than relying on an operator to manually turn a wheel. The heart of this improvement is the PID feedback control system. Let's trace back the process flow to see how this works. Fluid moves from the reactor V501 towards the first heat exchanger, E511A. In the past, keeping the temperature stable here will be difficult. Now we have installed temperature transmitter, marked here as T_1 and 1 and T_OUT 1. The PID controller continuously read the data from the sensor. For example, if T_OUT1 read a temperature that is too high, the PID controller calculate the error and immediately send signals to the upstream valve, BFV-101. The valve open or close slightly to adjust the flow rate measured by the F11 flow meter 1, bringing the temperature back to the set point. This ensure the process condition at the E511A and the subsequent exchanger E521 remain perfectly stable. So why did we choose this specific configuration? Manual valve cannot compensate for the sudden changes. By using the feedback from FM1 and FM2, the system automatically corrects disturbance, ensuring the output meets strict design specification. Previously, pump might run at full capacity regardless of the demand. With this automated system, if the thermal load at E5121 decrease, the valve restrict flow and the system consume less energy for pumping. The third is safety. The valve at the BFV-101 and BFV-102 are equipped with spring return actuators. This is a critical feature in the event of a power outage or system failure. This valve will be automatically snapped into a safe position, either fully open or fully closed, protecting the equipment and personnel. Finally, this setup shifts us from reactive to predictive maintenance. By integrating this component into the SCADA system, we can monitor the differential pressure across these heat exchangers. If we see a pressure drop that doesn't match the flow rate at FM1 or FM2, the system alerts us to early fouling or blockage before the equipment fails. By replacing manual feeds orifice designed with DPID integrated architecture, we ensure the facility operates with higher precision, better safety, and significantly lower downtime. So for conclusion, this case study aims to carry out a comprehensive analysis and review of the process control system currently applied in the premium vegetable oil industry. Our goal is simple: to recommend key improvements that drive maximum efficiency, safety, and performance. To achieve this, our group have adequately briefed on the planned operating procedure, process flow, and current control architecture. We conduct an in-depth study of critical areas, specifically focusing on interlock system, mechanism of temperature control, and deodorization practices and pressure control system. Through this documentation and organized selection of industry practice, we were able to spot specific deficiencies and inefficiencies in the current setup that holding the plant back. To close the gap, we are proposing three major state-of-the-art control solutions. First, we implemented the PID feedback control system to drastically improve temperature stability and response time. Second, we introduced motor-driven valve to modulate flow with far greater precision than manual operation. For the third, we are integrating smart sensor and PLCs. This allows for real-time data acquisition and better automation integration. We are also elevating our safety and maintenance standard. This includes the possibility of ultrasonic leak testing for predictive maintenance, ensuring we catch issues before they become hazard. We are also adding multi-level interlock to improve safety logic and installing bypass system around the heat exchanger to allow for efficient maintenance without shutting down the entire line. Beyond the technical aspect, this case study has highlighted the importance of well-organized teamwork and effective communication in solving complex engineering problems. So in summary, if this suggested change successfully implemented, the plant operational capabilities will be improved and its competitive position in the premium vegetable oil market will be significantly strengthened. Our goal is to make a substantial contribution to the efficiency and sustainable expansion of this industry.